That's very, so the idea is very clear that okay, we have millions of Gaussians. We will do the frustum queuing wherein we'll get thousands of Gaussians. Now we will break the scene into, we will divide the scene into tiles. We'll splat, we'll throw these 3D Gaussians on the tiles, and we'll project 3D to 2D projection, and then sorting based on the depth and alpha compositing. So that is the tile based rasterization. Now, if I talk about tile assignment, for each Gaussian, like here I have a Gaussian like this is the Gaussian. So for each Gaussian, we have to compute screen footprint, like what portion of screen that Gaussian, the 3D Gaussian is occupying. And I have to determine which tiles it overlaps. And whatever tiles that Gaussian is overlapping, we have to add Gaussian to tile list. So in this way, we are now very sure that okay, each tile will only process the relevant Gaussians. And this is very powerful technique, because out of thousands of Gaussians, it might be that a single tile might involve hundreds of Gaussians. And to process hundreds of Gaussians is like not very like a compute intensive task. So here we saw like how we are able to make, like how this tile based rasterization architecture is so efficient technique, and hence because of this efficiency which we achieved, we are able to process it in the real time, because this frustum queuing is like a very innovative process technique. And here you can see, like, out of so many 3D Gaussian, only the 3D Gaussian which are the part, the camera point of view, field of view, only those will be considered. And see this, the 3D Gaussians falling outside the camera field of view, they will be eliminated, like they will not be considered.